The basic idea of GANs is that you have two models, a generative model, which is called the generator, and a discriminative model, or the discriminator. The discriminative model has a task of determining whether a given image looks natural, and by natural I mean an image from the dataset, or it looks like it has been artificially created, or a fake image. This is basically a binary classifier that will take the form of a normal convolutional neural network, or CNN. The task of the generator is to create natural-looking images that are similar to the original data distribution. In order to use GANs, we need to have the following: real training images, which is the MNIST dataset here in this example, a generator network that takes in a random noise vector and produces a synthetic image, a discriminator network, which is a convolutional neural network, or CNN, that learns to distinguish between real and synthetic images. You can think of it as just a binary classifier, in which 1 is for the real image and 0 is for the fake image. An optimization procedure that jointly updates both networks through SGD, or a stochastic gradient descent. This is the tricky part, as we need to train the generator network to fool the discriminator network. And we need to have TensorFlow, which is our choice of deep learning. So let's get started. First, let's start with our imports. In this part of the code, we have imported TensorFlow, NumPy, Random, and Matplotlib libraries that we would be using in the next parts. Now we have to import our MNIST images. To do this, we'll call a TensorFlow function called readDatasets, as you can see here in this line. This loads in the 55,000 training examples in the MNIST database. The MNIST variable we created above actually contains both the images and their labels. Let's just isolate the image for now. There will be 55,000 images, and each of them will be of size 28 times 28. So here we have isolated the training images from the labels of the dataset that we have. We have got the shape of the training that we have. You can see that the shape is 55,000 samples and 784 features, which is 28 times 28. Now let's look at what a random image might look like. Here you can see one of the samples of the training set. Now it's time to design the architecture of the discriminator. Thus, we define a CNN classifier function that takes in an image of size 28 times 28 as input. The architecture of the deep convolutional neural network, or CNN, that we consider has 4 layers. As you can see, we have defined 4 different layers of convolutional neural networks and pooling layers. The first layer is a convolutional layer with a 5 times 5 kernel, 1 input channel, and 8 output channels, or output depth. And it is initialized by normal distribution. Here you can see the first layer architecture. So the weight kernel is 5 times 5. It is initialized by a normal distribution. The number of the input channels is 1 and the number of the output channels is set to 8. The bias is initialized with 0 value, as you can see here in this line. We will use the function tf.nn.conv2d through our code in order to get the convolution. It is actually the TensorFlow's function for a common convolution. It takes in 4 different arguments. The first one is the input volume. The next argument is the filter or weight matrix. Finally, you can also change the stride and padding of the convolution. You can see the function that I was talking about here. The input, the filter, the weight function, the strides, and the padding. Those 2 values, the striding and the padding, affect the dimensions of the output volume. Then the ReLU activation function is applied to the result of the convolution. The pooling is done by using tf.nn.averagePool function from TensorFlow library. The kernel for the pooling is set to 2 times 2, and the result would be the average of the input values lying in this kernel. You can see it here, the pooling. The kernel size is set to 2 times 2, and the stride is 2 times 2 as well. The other layers would be the fully connected layers. The first fully connected layer has 7 units, and since we have 2 dimensions, the total number of the weights that are defined here would be 7 times 7 times the number of the outputs, which is equal to 16. These are the parts that I'm talking about. So I skipped the explanation of the second neural network that we have here because it is the same as the first one. Nothing has changed. Just the input channels and the output channel has changed, and the number of the neurons that we have in this layer is different from the first one. The first one had 8 units, and this one has 16 units. Everything else is the same. So I was explaining the fully connected layer here. The number of the outputs of this fully connected layer is set to 32, and the ReLU activation function is applied on the multiplication of the flattened output of the previous layer, and the weights which is then added to this bias. The last fully connected layer will have 32 inputs and 1 output, which determines whether an input is a fake image, whether the output is equal to 0, or it's the actual or real one, which is equal to 1. This structure simply shows the binary classification using convolutional neural network. So this is the last layer, which is fully connected layer. It has 32 inputs and only 1 output, which would be 1 or 0 for 2 classes. You can see the output here.